Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for the final exam in a few weeks. So the topics and subtopics are listed here. I'm going to go through them in this order. So let's start with statistics. Let's start our statistics section by looking at a set of data. So hopefully you already know how to calculate mean, median, and mode, but I'll just go through it anyway. So the mean, usually called the average, is the sum of all the scores divided by n, which is how many there are. So if you add up all these scores, you get 628, and we divide by 8 to find the mean, because there are 8 scores, and that gives us 78.5. So let's now look at the mode. So the mode is the easiest to find. It's just the most common. So in the data above, 65 and 78 occur the most. They're the only scores that occur twice. So data can have more than one mode. So if it has one mode, we call it unimodal. And if it has two modes like this one, we say it's bimodal. More than two modes, we say is unimodal. And also remember, if no scores are repeated, then we say the data has no mode. So remember, to find the median, which is the middle score, we have to order the data from smallest to largest first. So let's quickly do that. So I've now put the 8 scores in order from smallest to largest. So remember, when there is an even number of scores, there will be two middle numbers. So the two middle numbers are these two. So when there's two middle numbers, the median is halfway between them. The median's the point in the data, so there are the same number of scores above it as there are below it. So when there are two middle numbers, the median is halfway between. If you don't know how to do that in your head, you can just add up the two numbers and divide by 2. That will give you the number that's halfway in between. So the answer here is 80. So that means that the median of this set of data is 80. So the mean, median, and mode are supposed to tell us about the center of the data. Remember, the range is something completely different. It tells us how spread out the data is. So the range of this data would be 90 minus 65, highest score minus lowest score, which is 25. It doesn't tell us about the center of the data, just how spread out it is. So what would happen if we added another score and it increased the mean to 80? What would that number be? So let's look at this question. So I said before that the mean is the sum of all the scores divided by how many there are. So that means that the sum of all the scores is just the mean times how many scores there are. So if I add another score, there will be 9 scores, and I want the mean to be 80. So if I add a score that increases the mean to 80, the new sum of all the scores will be 720, 80 times 9. So the numbers before added up to 628, I add another score, they now add to 720. So the new score would be 720 minus 628, which is 92. So if I add this score of 92, the mean will now be 80. So I did that by figuring out what the scores need to add up to. So that answers the question, what is the score? So what would be the new median? Well, if I add 92 onto this set of scores, there are now 9 scores. When you have an odd number of scores, there's only one middle score. So it would now be 82, because there'll be 4 scores above, 4 below. So for the median, we need to have the same number of scores above it as we do below it. So the new median here would just be 82. All right, how easy is that? So what we're going to do now is just have a quick look at skewness. So knowing the mean, median, and mode doesn't tell us that much about the data. So let's say I told you that the class average for this test was going to be 60%. Well, that doesn't tell us everything about the scores. They could have all been really, really close to 60. They could have all been 60. Or we could have had a situation where a lot of kids did poorly, some kids did really well and dragged the mean up, or the opposite. And that's what skewness tells us. So for skewness, we're looking at histograms. So remember, in a histogram, frequency is always the vertical axis, and we have bars for the different scores. The higher the bar, the more frequent it is. So if the mean of this test was 60, we could have a situation where we had lots of kids who scored lowly and then a few kids who scored highly to bring up the average. It could look something like this, the distribution of scores. It could look like this, where we have some kids did poorly, some kids did really well, but most kids were around the average. Or we could have the opposite of the first one, where there were only a few kids that did poorly, but lots of kids who scored highly. So, in order to talk about these situations, we've given them specific names. So, the first one, where you have a high frequency of scores closer to the minimum, scores clustered closer to the minimum, that is called positively skewed. So, remember, because of the way histograms are set up, with scores, down here would be the lower scores, here would be the higher. Lower to higher, lower to higher. That's the way number lines work. So the middle one, where you have the highest frequency scores in the middle, scores clustered towards the middle, that's called symmetrical. And we can see that there is symmetry there. So if we draw a line through here, one side is like a mirror image of the other. I'm sure you know what symmetry means. And then predictably, the final one is negative skew. So that's where you have a higher frequency of scores closer to the maximum. Okay, so it's important to note when we say high frequency of scores closer to maximum, we don't necessarily mean that these scores here are high. So if it was a test, you know, these scores could be in the 70s or something. Doesn't mean they're super high. It just means the highest frequency scores are closest to the maximum. Similarly here, it doesn't mean that these scores are really low, like 10 or something. It just means that the higher frequency scores are closer to whatever the minimum score was in the data. So for positively skewed, we usually have the mean greater than the median. So for symmetrical, the mean and the median are very close to equal. And for negatively skewed, we have the mean less than the median. So in the previous example where I gave a set of scores, the original mean was slightly less than the original median. So that had a slight negative skew. So make sure you understand this because it is a bit counterintuitive. You'd probably think more scores close to the maximum would be a positive skew, positive because higher, but it doesn't work like that. So make sure you understand this. All right, next we go through probability. So we turn our attention to probability, and we'll start with this question. Class of 30 students, 18 brown hair, 7 blue eyes, 10 neither. And we select a student at random. We're going to find some probabilities. So hopefully you remember probability is assigning to random events a number between 0 and 1 to indicate how likely it is to occur. So whenever you are asked what is the probability of blah, 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 you need to give a number between and including 0 and 1. Of course, numbers close to 0 have a low chance of happening. Numbers close to 1 have a high chance of happening. So it doesn't matter whether you give your answer as a decimal fraction or percentage as long as it's a number between 0 and 1. So this question here is asking about different categories. We're looking at people who are in the category of brown hair, people who are in the category of blue eyes, or people who are in both categories or neither category. So whenever you're asked about two categories like blue eyes and brown hair, or we could be talking about, you know, born in Australia, play soccer, whatever the categories are, whenever you're asked questions about two categories, think Venn diagrams and two-way tables. They're a convenient way to display the information. So before I answer the probability questions, I'm going to put up the information in a Venn diagram and two-way table. So it doesn't matter which one you use because they do exactly the same thing. So let's first look at a Venn diagram. So they look like this, and there are two circles for the sets or the categories. So the two sets we have here, blue eyes and brown hair. Okay, so I better specify that that's here. So what we do for Venn diagrams, we have four numbers that go in these four boxes. We populate them, and that'll help us with the probability calculations. So notice 18 plus 7 plus 10 is more than 30. So that actually equals 35, but that's still possible. How? it means we've double counted 5, because 35 is 5 more than 30. So double counted 5 means that there were 5 people who were included here in brown hair, and were also included here in the blue-eyed category. So however many you have double counted goes in the middle. That's how many have both. 5. So there were 7 people with blue eyes. There's already 5 in the blue-eyed circle, so I need another 2 to go there. So there were already 5 in the brown hair circle, so I need 13 more to make 18 in the brown hair circle in total. And as it said in the question, 10 had neither. So note, 10 plus 13 plus 5 plus 2 does equal 30, so we know we've done something right. So we could also display this information in a two-way table. So we have 2 ways. The first way is the eye color, where they have blue eyes or blue eyes dash. The dash means not blue eyes. Of course, the other way in the two-way table will be whether they have brown hair or not. So, unlike Venn diagrams, two-way tables usually have a row and a column where you write in the total. So, we'll do that here. So, the 4 main cells here, these 4 boxes here, have the same numbers as the Venn diagrams. So, this box here is blue eyes and brown hair, which we found was 5. This box here is brown hair but not blue eyes, so these 13 people here. Down here, blue eyes but not brown hair, these 2 people here. And the last box is not blue eyes, not brown hair, those people outside the circles in the Venn diagram. So notice these 4 numbers here are the same 4 numbers as in the Venn diagram. So the totals, you can just add them up. They should all add to 30 because there were 30 people in total in this, okay? So the Venn diagram and two-way table display the exact same information. You can pick whichever one works for you in the test. Just make sure you know how to do at least one of them. So let's go ahead and answer the probability questions. So what's the probability a student has blue eyes but not brown hair? Well, that's easy. We can see here there are 2 of those people from the Venn diagram and the two-way table that have blue eyes but not brown hair. So it'll be 2 out of 30 or 1 out of 15. So what's the probability a student has blue eyes or brown hair? So when we say blue eyes or brown hair, we mean blue eyes or brown hair or both. We have to include both. So these people here have blue eyes or brown hair or both, so do these and these people. We add up the 3 numbers inside the circles. For the two-way table, we're looking at these people here. They have blue eyes or brown hair, so do these and so do these. So 13 plus 5 plus 2 is 20 out of 30, which simplifies to 2 out of 3. Okay, so again, notice I gave a number between 0 and 1. So or includes all the people that have blue eyes, all the people that have brown hair. All right, so the last one's a bit tricky. What is the probability that they have brown hair if I know they have blue eyes? So if I know they have blue eyes, I'm in this circle here. So there are 7 people to choose from, and of those 7 people, 5 of them have brown hair. So 5 out of the 7 people with blue eyes have brown hair. So from the two-way table, we see here if blue eyes, we're in this column here. There are 7 of those. How many of them have brown hair? And that's 5. So that's how I got the answer 5 out of 7. So remember, two-way tables and Venn diagrams are all about displaying information about different categories. We're now going to look at tree diagrams, which are used for a different purpose. So let's look at this question here. I picked 2 cards from a deck, one after the other with replacement. What's the probability each card is a different suit? So in the previous question, I was looking at more than one category. I was looking at whether something is in this category, blue eyes, or in this category, brown hair, or both or neither. So here what I'm doing is a multi-stage experiment. That's what tree diagrams are for. I'm not worried about categories and what category something is in. What I'm doing is I'm doing an experiment with some outcomes. then doing another experiment with some outcomes, and tree diagrams allow me to list all of the possible outcomes. So this is a multi-stage event. The 2 stages are picking the first card, that's the first stage, and picking the second card, that is the second stage. So what we have here, first stage, we list the outcomes, and second stage, we list the outcomes, and then we list the outcome and probability. So for the first stage, if I'm picking a card, there are 52 in a deck. I don't want to write out all 52 possibilities because I'm only interested in the suit of the cards. So in that regard, there are 4 outcomes. I could get a heart, a spade, a diamond, or a club. Similarly, if I get a heart on the first go, I can get a heart, a diamonds, a spades, or clubs on the second go. That's the same for all of them. So again, the goal here with the tree diagram was to list all the outcomes. So I'm going to do that under the column out. So follow the branches. So first go, of course, I can get hearts, spades, diamonds, or clubs, and I can get each of those on the second go. So I can get hearts, then hearts, so that's HH. I can get hearts, then diamonds, and so on. So there were 4 outcomes on the first go, 4 on the second go. So the total number of outcomes should be 4 times 4, or 4 to the power of 2. If I were to draw 3 cards, the number of outcomes would be 4 to the power of 3, 4 times itself 3 times. So I'm listing all of the 16 outcomes. This will make probability questions so much easier. So again, there are 16 outcomes because there are 4 by 4 outcomes. So I don't need to put probabilities on branches here or anything because each outcome is equally likely. The first go, hearts, spades, diamonds, and clubs are equally likely. Because the card was replaced, so that means it was put back in the deck, on the second go, hearts, diamonds, spades, and clubs, they are all equally likely. If you got a spade the first go, hearts, diamonds, spades, and clubs are still all equally likely. So all of these have a probability of occurring of 1 out of 16. They're all equally likely. So figuring out the probability that each card is different suit is now going to be very easy. I just have to go and circle all the ones, like this one here, where each card is different suit. So that was hearts and diamonds, different suits. The next one, hearts and spades. That's a favourable outcome. And so on. I keep doing this. So circled in yellow are all the outcomes where each card's a different suit. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. All but 4 are circled. So the probability each card is a different suit is 12 out of 16. That would have been quite hard to figure out without the tree diagram. So, of course, 12 over 16 simplifies to 3/4. So there is a 3/4 probability that the cards I pick will be of a different suit. So that was an example of with replacement. So that's where the object taken the first time is put back, or in other words, the probability of getting something the second go is the same as the first go. Probability of getting hearts was 1/4 on the second go, the same as it was on the first go. Now we're going to do one that is without replacement. Chocolates containing Mars bar, Crunchy, and Boost. 2 chocolates are taken and not replaced. What is the probability that a Boost is not taken? So this is a pretty difficult question to do right now because we don't know all of the outcomes and we don't know how many of them don't include a Boost. So what we're going to do is draw a tree diagram to list all the outcomes. So there are 2 chocolates being taken, so 2 stages. The first chocolate and the second. And then we will list all the outcomes. So first go, we can get a Mars bar, a Boost, or a Crunchy. Now, if the Mars bar is taken, that only leaves a Boost and a Crunchy. If the Boost is taken, only leaves a Mars bar and a Crunchy. And if the Crunchy is taken, that only leaves a Mars bar and a Boost. So these are the 6 possible outcomes. That's why we did the tree diagram, so that we could list these 6 outcomes nice and easily. It's hard to come up with these off the top of our head. Now, all the outcomes at each stage are equally likely. So these 3 outcomes, Mars, Boost, and Crunchy, are equally likely. The second go, Boost and Crunchy are equally likely. So we don't need to put any probabilities on the tree. So in the test, there won't be any questions involving putting probabilities on the trees. So that at each stage, each outcome will be equally likely. So now it's just a case of counting. What's the probability a boost isn't taken? So this is one where we didn't get a boost, and this is another one where we didn't get a boost. So what's the probability a boost is not taken? 2 out of 6 or 1 out of 3. Okay, we could answer other probability questions about this. What's the probability that I get a Mars bar and a Crunchie? That would also be 2 out of 6 or 1 out of 3. It'd be the exact same question, exact same outcomes. So that's what tree diagrams are for, listing outcomes in multi-stage events. All right, we now turn our attention to index laws and scientific notation. So these are the 7 index laws you need to know, but just before I go through them one by one, we need to make sure we're on the same page. So remember, if you have something like 4 to the power of 5, this larger number here is called the base, and the smaller number is called the power or the index. So the index tells you how many times you're multiplying the base by itself. So 4 to the power of 5 means you times 4, the base, by itself 5 times. So 4 to the power of 5 is not 20. It's actually 1024. So this here, where we actually write out the product, is called expanded form. And this here, where it's something to the power of something, is called index form, because the power is also called the index. Okay, so I'm going to refer to bases in this. So let's go ahead and look at our index laws. So the first one is saying when I multiply bases, I keep the same base and add the powers. So if I have something like x to the power of 7 by x to the power of 2, keep the same base, add the powers. The second one says, if you're dividing bases, keep the same base and subtract the powers. So if I had something like y to the power of 13 divided by y, note y is the same as y to the power of 1. That would be keep the same base, subtract powers. The third one is power to a power. If you raise a power to another power, you keep the same base and multiply the powers. So if I have something like x to the power of 4 and I raise that to the power of 5, keep the same base, multiply the powers. So the next one says that anything that is not 0 when raised to the power of 0 gives 1. So that means like 2 to the power of 0 is 1. 3 to the power of 0 is 1. 4 to the power of 0 is 1. Anything except 0 to the power of 0 is 1. 0 to the power of 0 is actually undefined. But anything else, like 4 to the power of 0 minus 2 to the power of 0 is 1. So number 5 says that if you take a product and raise it to a power, the power of the product is the product of the powers. You raise each thing in the product to the power. So if I had something like 2x to the power of 3, I raise the first thing to the power and the second thing to the power. You can write that as 8x cubed if you like. Number 6 says if you have a fraction to a power, raise the top, the numerator to the power, raise the bottom or the denominator to that power. So if you had something like x over y to the power of 4, raise the top to that power, raise the bottom to that power. And the final one says if you have a negative power, it goes on the bottom of the fraction, but you write it with a positive power. So if I have something like 2 to the power of negative 3, that's the same as 1 over 2 to the power of positive 3. I just moved it to the bottom of the fraction. So I'm just going to go through a few quick examples on the next slide where you have to use more than one index law. So let's go through these examples. So starting at the top. So if you have numbers separate from the bases, treat them separately. So 3 times 2 is 6. X to the power of 4 times x to the power of 7. Keep the base, add the powers. And I haven't done anything yet to the denominator. Okay? So again, I'm going to treat the numbers separately. 6 divided by 6 is 1. X to the power of 11 divide x to the power of 5. Keep the same base. This time subtract the powers. So the answer is just x to the power of 6. Second one. So now I've got a product and I'm also using the power to a power rule. So what we do is we raise the first thing to that power and we raise the second thing to that power. So x squared to the power of 4, keep the same base, multiply the powers. So that's 81x to the power of 8. That's as simplified as it can get. When you have something like this with a few negatives, everything with a positive power goes on top. Everything with a negative power goes on the bottom, but you write it with a positive power. So how we do the last one? So the first one is using that product rule. I'm raising everything in the brackets to the power of 0. So this bracket here will just be 1. Here, in the second one, I'm not raising everything to the power of 0. I'm just raising k to the power of 0. So that part will be 3 times 1. Only the k is getting raised to the power of 0, and anything to the power of 0 that's not 0 is 1. So the answer here would be 1 plus 3, which is 4. Okay, and I'm done. So now I'll quickly show you how to put numbers in scientific notation. So scientific notation is when you have a really large number or a really small number and we want to write it in a more convenient way. So remember what we do is we write it as something, some number between 1 and 10 times 10 to the power of something. So what we do is we take our number, in this case we'll look at the first one, which is a big number, put our decimal point there. What we do to fill the first box is we move the decimal point until the whole number is between 1 and 10. So if I move the decimal point here, I get the number 1.728564. That is between 1 and 10. I want to write this number as 1.728564 times 10 to the power of something. So what goes in the second box is the number of places that you moved the decimal in order to make the number between 1 and 10. Okay? So to take this really big number here and make it between 1 and 10, I move the decimal point 3, 6, 9 spots. So a 9 is what goes in the second box in the power. So let's look at the second number below. So this is now a really small number that I want to put in scientific notation. So same thing, I'm going to move the decimal point 3, 5, 6 spots to make this number 3.625. It is now a number between 1 and 10. So it's going to be 3.625 times 10 to the power of... Now, I moved the decimal point 6 spots, so I put a 6 here. But the thing is that 3.625 times 10 to the power of 6 is a really large number. If I move the decimal point right, then it actually needs to be a negative in the power. Added that rule here. The number that goes in the power box, which is always a whole number, it is positive if you moved the decimal point left to make the number between 1 and 10. It is negative if you had to move the decimal point to the right. In other words, the number that goes in the power box is positive if it's a large number, if it's more than 1, and it's negative if it's a small number, if it's less than 1. Okay, so make sure you get that right. So you can always check your answers, like put this on your calculator and put this on your calculator, and you should get the original number. That works as long as the power isn't too great. If it was, like 1.8 times 10 to the power of 30, your calculator wouldn't be able to show you that number of digits. But you can always try and put your answer on your calculator and see if it gives you the original number. All right, let's now look at similarity. So two shapes are similar if pairs of corresponding angles are equal and pairs of corresponding sides are in proportion. So for two shapes to be similar, they have to have both of those, sides in proportion and angles equal. So similarity basically means if two shapes are similar, one is just an enlargement of the other. So let's have a look at this triangle here. So if I make an exact copy of this triangle, these two shapes are congruent. So congruent means they are the same shape and same size. Similarity basically means they're the same shape, but not necessarily the same size. So I might go and enlarge this triangle. It doesn't matter if I rotate it as well. These two will be similar. One is just an enlargement of the other. I just took it and I stretched it in all directions. So that's what it means that the two shapes are similar. So it means that corresponding angles will be equal. So this angle and this angle will be equal, this angle and this angle, and this angle and this angle will be equal, and corresponding sides will be in proportion as well. So it's important we know how to line up the vertices. So if I call this triangle ABC, and this becomes triangle D, E, and F, the way that we write that they're similar, triangle ABC is similar to, we can use that notation or we can use this symbol. Either way, it doesn't matter. And you've got to line up the vertices. So A corresponds to D because the angles are equal there. B corresponds to F and C corresponds to E. That's how we write a similarity statement. So now we're going to look more at these two conditions. So it's actually possible to have two shapes that have their sides in proportion but not equal angles. So let's look at these two shapes here. So the first one here got the computer to give me a rectangle. So it has all right angles. The second shape is a parallelogram. So because it's a parallelogram, this side here will be 14 and this will be 8. And in the first one, this will be 7 and this will be 4. So the sides are in proportion. How do I know that? I can check each side divided by its corresponding side. 14, this side, which corresponds to this one, the two longest sides correspond. 14 over 7 equals 8 over 4. 8 divided by 4 gives you 2. So each side in the parallelogram is double its corresponding side in the rectangle. So the sides are in proportion. But clearly they don't have the same angles because this parallelogram doesn't have right angles. Those two are the same and those two are the same. But the angles are not equal between the rectangle and the parallelogram. So therefore these two shapes are examples of shapes that are not similar, even though their sides were in proportion. So what I want you to understand is that triangles are a special case. This could never happen with triangles. I can't draw two triangles whose sides are in proportion but have different angles. So triangles allow us to get away with a bit more. So, even though this doesn't work for quadrilaterals as I've just shown, if three triangles have all their sides in proportion, then they will be similar. I don't need to check their angles. So that's what the SSS test is about. It says if three sides are in proportion between two triangles, they will be similar. Okay, so S means side in proportion. There are three other tests, SAS. So make sure you understand that means two sides are in proportion and the angle between those two sides is equal. It has to be the angle between the two sides in proportion. The next test is AAA. So that's saying if you have two triangles and all their angles are equal, they will be similar. I don't need to check whether or not their sides are in proportion. I just know they will be. And the last test is RHS. So RHS means R right angle, H hypotenuse in proportion, and S means another side in proportion. So you need to be able to use these tests to determine whether or not triangles are similar to each other. Let's look at some examples. So let's look at these two triangles here. Are they similar? Well, you've got to line up corresponding sides. Longer side with longer side, and then the shorter side with shorter side, and see whether these numbers equal. So if you put 12 over 8 on your calculator and 10.5 over 7, you get the same number, 1.5. So these two pairs of sides are in proportion. The angle between them is also equal. So this is an example of two triangles that are similar by the SAS test. So let's now look at these two triangles. Well, they both have a right angle, and 3 over 2 is equal to 1.5 over 1. Both of them, again, equal 1.5. So we have two sides in proportion. Now the angle between them isn't equal. We don't know yet whether this angle here and this angle here are equal, so we can't use the SAS test. But because they both have a right angle, the hypotenuse is in proportion, and another side is in the same proportion, we can use the RHS test. So these two triangles are similar by the RHS test. So note, this test here, and this test here all involve pairs of sides. You need at least 4 side lengths, at least 2 pairs of side lengths to use any of these tests for similarity. You need 2 pairs of sides to determine whether they're in the same proportion, whether the scale factor is the same. If you don't have 2 pairs of sides, your only choice is to use the AAA test. So if we had something like this, 2 triangles here, let's say these 2 lines are parallel, these 2 triangles, the smaller and the larger one, would be similar by the AAA test. I can't use SSS, SAS, or RHS on these 2 triangles here. There's not enough information about sides. But because the lines are parallel, this angle and this angle are corresponding, they'll be equal. This angle and this angle are corresponding, they'll be equal. And this angle is common. So these 2 triangles will share the same set of angles, so they will be similar by the AAA test. So let's look at this last triangle here. Well, I have a pair of sides here, 2 and 4, and I have another one. But I don't have enough information to use any of the tests involving side lengths. I don't have 2 pairs of side lengths. I can't compare the 4 and the 2, the scale factor of 2. I can't compare that to another pair of sides. So my only choice here is AAA. So this angle here and this angle here are equal because they are alternate. Similarly, this angle here and this angle here are alternate. And the 2 angles in the center are vertically opposite. So there are 3 pairs of equal angles. These 2 triangles are again similar, not equal. They are similar by the AAA test. So now let's quickly look at finding unknown sides using similarity. So here we have 2 triangles that are again similar by the AAA test. I've marked the 3 angles for you to tell you that they're similar. So because all 3 angles are equal, these 2 triangles are similar, meaning sides will be in proportion. So we need to line up corresponding sides. So the 12 and the 5 correspond. You can see they have the same angles touching those sides, the X and the dot, right? So the number we times by sides in the smaller shape to get sides in the larger shape is called the scale factor. So I said always do the scale factor as the side in the larger triangle divided by its corresponding side in the smaller triangle, because that makes it very clear whether you need to times or divide. So if you said the scale factor here was 5 over 12, it's not wrong, but you wouldn't be able to follow the rule that I'm about to show you. So I'm saying scale factor, larger side divided by smaller side is 2.4. So 2.4 is what you multiply the sides in the smaller triangle to get their corresponding sides in the larger triangle. So the rule is if you want to find a side in the larger triangle, then what you do is you times by the scale factor. You take the side in the smaller triangle and times by the scale factor. And if you want to find a side in the smaller triangle, you divide by the scale factor. Okay? So if you do the scale factor as the larger side, the side in the larger triangle divided by its corresponding side in the smaller triangle, then you can always use this rule that you times to find a side in the larger shape and you divide to find a side in the smaller shape. So following this rule, y is in the larger shape, so I take its corresponding side in the smaller one and I times by the scale factor and I just get 15. Following this rule, if I want to find x is in smaller triangle, so I take its corresponding side in the larger one and divide by the scale factor, and I get 7.5. So that's how we can use similarity to find unknown sides. I'm just going to do one example that's a little harder. So let's try and find the value of x in the diagram here. So the two triangles, the smaller and the larger, they will be similar, again, by the AAA test. They both have a right angle, and this angle here is common. So if two triangles have two pairs of equal angles, the third pair of angles will also be equal because they must add to 180. So these two triangles will be similar by the AAA test. So that means all sides will be in proportion. So the scale factor here, it's not 5/4 because 5 is not the side of a triangle. It's the side of a quadrilateral. The scale factor, this whole side here is 9 divided by the side in the smaller one, which is 4, 2.25. So that's scale factor. So now I want to find x. The problem is I don't know its corresponding side in the larger triangle. So I'm going to have to set up an equation. So the side in the larger triangle is x plus 3. So I know that that is going to be 2.25 times the side of the smaller triangle. So now I need to solve this equation. So I'm going to subtract x from both sides and divide each side by 1.25. And if I divide 3 by 1.25, I get x is 2.4. Okay, so that was a slightly harder example, but you need to be able to do that for the test. All right, we're going to go through the last topic now, which unfortunately will take the longest to go through, and that is quadratics. So we start by looking at expanding, in particular doing binomial expansions. So expanding is when you have something like this that has brackets and you end up with something without brackets. So you should know how to do this from earlier in the year. Even in year 8 you would have done it. So to expand this, we use the distributive law. Take the thing outside the bracket, distribute it to the first thing, times, do the same for the second, distribute it to the second thing. X times minus 2 is minus 2x. But we've taken it a step further, and we've done binomial expansions where you have two sets of brackets, where I have something like this, x plus 4 times x plus 1. When we expand this, we get a quadratic because it has an x squared term. So we use the method FOIL. So remember, f was first. So if I'm going to do that, f is x times x, the thing that comes first in each brackets. Then O, outsides, the thing on the outside of each bracket. So that's x times positive 1. Then I was the two things inside the bracket. So that's 4 times x. And then L is last, the thing that comes last in each bracket. So 4 times positive 1 is positive 4. Okay, so when you're using the FOIL method, you'll often have like terms in the middle there. So x squared is not a like term. I leave it as it is. X plus 4x gives 5x. And that is my final answer after I've done that. So let's look at one with negatives. If I have x minus 3 times by, let's say, x plus 2, same thing. Firsts, thing that comes first in each brackets. Outside is x times positive 2. Insides is negative 3 times x. And lasts is minus 3 times 2. Again, collecting like terms in the middle, I get x squared minus x minus 6. So when you have something like x minus 5, x plus 5, we've got the same thing in each brackets, but one has a plus, one has a minus. You can use FOIL for this like I did on the previous example, but there is a quick way. This is called the difference of two squares. So you square the first, square the second, and stick a minus between them. That only works when you have the same thing in each brackets, but one has a minus and one has a plus. That's the quick way to do it. If you have a perfect square like this, remember, squaring something is the same as timesing by itself. So I can write it like this. So you can expand this using FOIL. The quick way to do perfect squares is square the first, square the second, always positive, and what goes in the middle is 2 times 3 times x, 2 times the product of the two things in the brackets. So 2 times 3 times x is 6x. That's the quick way to do it. Now, you don't have to use the quick way for any of these. You can use FOIL. So the quick way to do two different brackets like x plus 5 x minus 7. You have x squared. So 5 minus 7 is the number that goes in front of x. So the coefficient of x is the two numbers added together. So 5 plus negative 7 is minus 2. And the number that goes by itself is 5 times negative 7. The two numbers multiplied together, okay? So that was the quick way to do it. If you didn't want to use the quick way, again, you could have used FOIL. So just note, sometimes you'll get something like this, where I have like 2x plus 1 times x minus 5. There's no quick way to do that. We'll just have to use FOIL. 2x times x is 2x squared. 2x times negative 5. 1 times x. 1 times negative 5. And again, collect the like terms, okay? So all of these answers can come from using FOIL, but there are some quick ways to do some of these calculations. It's up to you whether or not you want to use them. All right, so that's expanding. Let's look at the opposite now, which is factorizing. So if we had something like x minus 3 times by x plus 8, if I use FOIL and go ahead and do that, so I can go x squared, the number in front of x will be 8 minus 3, or minus 3 plus 8, and the number by itself will be minus 3 times 8. So this way was what I just did. Using FOIL, started with brackets, ended up with something without brackets. So that's expanding, which I just showed you. We're now going the other way. We're factorizing. So what that means is I am taking an expression like this, and I'm writing it as something times something. That's what it means to factorize. So there were different methods of factorizing you would have learned, and you use different methods depending on whether it's a binomial or trinomial. When it's a quadratic binomial, that is when there are two terms, you use highest common factor or difference of two squares or both. So let's say we have something like x squared plus 4x, okay? This has two terms, x squared and 4x. So each of these terms has a common factor of x. So we're going to use highest common factor method. So you take the highest common factor out of the brackets. Inside the brackets, you divide each term by the highest common factor. So x squared divided by x is x. In other words, what do you times by x to get x squared? Answer x. What do you times by x to get positive 4x? The answer is positive 4. So if you expand this, you get that, because factorizing is the opposite of expanding. So if I have something like, I don't know, 2x squared plus 8x, the highest common factor, they both have an x, but they also have a highest common factor of 2. So what do I times by 2 to get 2x squared? X. What do I times by 2x to get 8x? Again, positive 4. Okay? And if I expand that, I get that. So sometimes you'll get expressions like this, x squared minus 9. This is the difference of two squares. It is a square minus a square. So when that happens, two brackets, square root the first, square root the second term, one gets a plus, one gets a minus. Because I showed you when we were expanding using FOIL, the quick way to expand this is square the first, square the second, and stick a minus between it. We're just doing the opposite of FOIL. So if I have something like 4x squared minus 25, it's the same thing. It's a perfect square minus perfect square. Two brackets. Square root the first. So the square root of x squared is x. Square root of 4 is 2. So 2x in each brackets. Square root of 25. One gets a plus. One gets a minus. Okay, and again, if I expand this using FOIL, I will get that. So sometimes you have to use both. So let's say I have something like 2x squared minus 50. 2 is not a perfect square and 50 is not a perfect square. So what I'm going to do is use highest common factor here. Now note, in this example and this example, there were no common factors. X squared, negative 9 have no common factors. 4x squared and negative 25 have no common factors. But here, in this one, they do. So we take the highest common factor out of the brackets. So what do I times by 2 to get 2x squared? X squared. What do I times by 2 to get negative 50? It's minus 25. So note, this thing in the brackets, x squared minus 25, is the difference of two squares. So I'm going to use that. Two brackets, 2 didn't go anywhere. Square root the first, square root the second, 1 gets a plus, 1 gets a minus. That's how we did binomials, things with 2 terms, but you also need to be able to factorize trinomials with 3 terms. And the way we do them is a little different. So what we do is if we have something like, let's say, x squared plus 8x plus 15, we're undoing FOIL. So remember the trick I gave you? If you're expanding brackets, these two numbers added together give you the coefficient of x. The two numbers multiplied together give you the number by itself. So we're going to undo that. What we're going to do is we're going to put an x in each bracket, and the two numbers that go with it are two numbers that add to give the number in front of x and times to give the number by itself. So the two numbers that add to 8 and times to 15 are 5 and 3. Positive 5, positive 3. So that's how I factorize it. Let's say I have x squared minus 6x plus 9. So two numbers multiply to positive 9 but add to negative 6. So those numbers are minus 3 and minus 3. Okay? Let's say it's something like x squared minus 10x plus 24. So I'm undoing FOIL. So I get two brackets with an x in. I want two numbers that times to positive 24 and add to negative 10. So if I don't know what those numbers are, go through factors of 24. It turns out they're going to be minus 6 and minus 4. Let's say I had x squared minus x minus 20. So now I want two numbers that multiply to negative 20 and add to minus 1. So I put an x in both brackets. The two numbers that multiply to negative 20 and add to minus 1, 5 and 4. Now, because they're multiplying to minus 20, one has to be negative, one has to be positive. Because they add to minus 1, then 5 has to be negative and the 4 positive. Okay? So if you're stuck, go through factors of the constant term. All right? So make sure you practice with this. So that's factorizing. Let's now have a look at solving quadratics. So remember the process for solving. One side of the equation has to equal 0. That'll usually be done for you. Then we factorize, then we use the null factor law. So if you have something like x squared plus 7x plus 12 equals 0, don't try and get x by itself by subtracting 12 and dividing by 7. You will get nowhere. You'll be there all day and you won't get anywhere. Follow these steps. So one side is equal to 0 already. Now we factorize this. So this is a trinomial here. So I want two numbers that multiply to 12 and add to 7. So if you don't know, go through factors of 12. Should get 3 and 4. So null factor law, either the first thing is equal to 0, which would mean x is minus 3, or the second thing is equal to 0, in which case that would mean x is minus 4. So the two solutions to this equation are minus 3 and minus 4. If I substitute them for x in this equation, I get a true statement. So let's say I have x squared minus 25 equals 0. So one side's equal to 0. Factorize. This is a binomial. It's difference of two squares. So square root the first, square root the second. One gets a plus, one gets a minus. So either the first bracket is equal to 0, which would mean x is minus 5, or the second thing is equal to 0, in which case x is 5. So let's say I had something like 3x squared minus 18x equals 0. Same process. Factorize, so this is highest common factor. 3x times x gives x squared. 3x times negative 6 gives negative 18x. So either the first thing is equal to 0, which would mean x is 0, or the second thing is equal to 0, which would mean x equals 6. Okay, so usually the quadratics have two solutions, sometimes they don't. So if I had something like x squared minus 12x plus 36 is equal to 0, same process, we've got one side equal to 0. Second step is factorize. So I want two numbers that multiply to positive 36, add to negative 12, and they will, of course, be -6 and -6. So because I got the same number, because each bracket is the same here, this will have only one solution. X minus 6 equals 0 means x equals 6. That's the only solution. Okay? So that's how we solve. It's the same as factorizing. We just go one extra step and use the null factor law. So remember, the null factor law is if two things multiply to give 0, either the first thing is 0, the second thing is 0, or both are 0. And that's what we've been using here. All right, the final thing we need to go through is graphing quadratics. So the graph of a quadratic is a parabola. So we're graphing things of the form y equals x squared plus something times x plus something. So remember, parabolas always have a characteristic shape. They are either a smiley face or a frowny face. We're really only looking in the test at smiley faces the right way up. So they are curved. They're not straight lines. So we're looking at the Cartesian plane. So all parabolas have this basic shape, and we need to make sure you know the features of a parabola. So this is actually the graph of y equals x squared minus 9. So every parabola, as I said, is either this shape or this shape. We're just looking at the smiley faces. So it is a curve. There are no straight lines here. So every parabola, aside from having that shape, also has a y-intercept. It always hits the y-axis somewhere. So the y-intercept here is 0, minus 9. They're the coordinates of the y-intercept. So it's supposed to be like this. It hits it there. Okay? So parabolas can have 1, 2, or 0 x-intercepts. That depends on how many solutions they have. So this one actually has 2 x-intercepts. One at -3, 0. So that's that one there. And it has another x-intercept there at 3, 0. Okay? So the fourth thing, the turning point and axis of symmetry. So every parabola has a turning point where it's like going down, it'll stop and turn around. So the turning point here is actually the same as the y-intercept, which is 0, minus 9. So that's not always the case that the turning point of a parabola will be the y-intercept. It was just like that in this case. Now, parabolas are symmetrical. So there will be a line you can draw right through the middle of the parabola that's an axis of symmetry. It's symmetrical about that line. And I'm sorry if it doesn't look like that from my poor drawing. So the axis of symmetry is a vertical line. We learned earlier in the year that vertical lines in the Cartesian plane have the equation x equals a number. So that number will always be the x coordinate of the turning point. So the axis of symmetry, this line here, is x equals 0. Okay, so it's important that you can identify those features of a parabola. Aside from the shape, which is a curve and never a line, the y-intercepts, which there always is one, x-intercepts if there are any, and also the turning point of and axis of symmetry. All right, the very last thing we're going to do with parabolas here is I'm going to start with an equation and turn it into a graph. We're going to graph the equation y equals x squared minus 4x. So I taught a way to graph this where we go through and find the 4 features and plot them. So firstly, as I said, we're only going to be looking at ones that are smiley faces, so it'll be this shape. Because the number in front of x squared is positive, it will be a smiley face. So the second thing that we look for is the y-intercept. So the y-intercept is the y value when x equals 0. So here, the y-intercept will be x squared, which is 0, minus 4 times 0, which is 0. The y-intercept here is 0, because when x equals 0, y equals 0. So the third thing is the x-intercept. So what we do is we let y equal 0. So to find the y-intercept, you let x equal 0. To find the x-intercepts, you let y equal 0. So we take our equation here, and we change y to 0. That's just solving a quadratic, which is what I showed you how to do on the previous slide. So factorize this. This is using highest common factor. So either the first thing is 0 or the second thing is 0. So if x minus 4 equals 0, x equals 4. So the two x-intercepts are 0 and 4. So finally, the turning point and axis of symmetry. So the turning point is halfway between, the x-coordinate of the turning point is halfway between the two x-intercepts. So it will be 2. When x is 2, y is 2 squared minus 4 times 2. Put that on your calculator, you get minus 4. So the turning point is 2 minus 4, which means the axis of symmetry will be the vertical line x equals the x-coordinate of the turning point. Okay, so they are the features we found. So the orientation will always be a smiley face. Secondly, you find the y-intercept by letting x equal 0. Thirdly, you find the x-intercepts by letting y equal 0. And fourth, you find the turning point. The turning point, the x-coordinate is always halfway between the two x-intercepts, and then you find the y-coordinate of the turning point by substituting into the original equation. And when you have the turning point, the axis of symmetry is easy. It's just x equals the x-coordinate of the turning point. So when you have all these, let's turn it into a graph. So here's our Cartesian plane all ruled up, and we're just going to plot these features. So we can't plot the orientation, the first thing, but that'll become apparent when we plot the others. So the y-intercept was 0. That's also one of the x-intercepts. So we put a dot there. The other x-intercept was at 4. The turning point was 2 minus 4, which is down here. We've plotted these things. Because we know the orientation is like this, it's obvious what it will look like. Let's just join them up in this sort of shape. Sorry for my poor drawing, but that's what it will look like in green. So again, it is curve, it is not straight lines. So you can go through that process for any parabola we give you, find those 4 things, plot them and join them up, and you should get a nice curve. Okay, I'm sorry for the long video, but that is it. That's all you need to know for the final test. I hope you're not stressing about it because you're a superstar and you're going to ace it. There's heaps of help. There's tutoring, practice exams. Go through them. Ask me for any help you need because I want to see you do well, and I know you will do well. This has been the luckiest maths teacher in the world. Have a great day.